Okay. Okay. So I'll be doing all these recursion problems today. These are pretty standard problems, and you can expect them in your interview like if somebody's asking a problem on recursion, then definitely these are the ones, these are the most frequently asked recursion questions. So I'll be just doing this, especially I think a lot of people struggle with recursion, and you know to solve recursion problem, it's somehow, it's similar to how you solve a DP problem as well. But yes, so basically thinking wise, somewhere you can say that some steps are very similar to how you solve a DP problem, but still recursion uh, is how you like you need to have faith in recursion. So if, let's say, let me just start solving and then we can discuss it. Okay, let me reset this timer. So permute, right? So basically, to solve a recursion problem, I think you don't need to think about the whole recursion tree which will form. Otherwise, I think if you sit and start drawing uh, every recursion problem's tree, we'll never be able to solve a question, because the possibilities are just, there is insane amount of possibilities, and you can never come to a definite conclusion. So that's why you need to visualize how recursion works, and you know even if there is a new problem coming up, you can tackle that by approaching it with a similar mindset. Basically, that is the idea. So this problem is permutations. I think it's pretty standard problem. I think this is one of those very first problems which you'll, while learning recursion, you'll do that, right? So let's take something like a helper function, and we need to give vector of vector as an output. So let's try this. Okay. So basically, today I'll not be explaining a lot of stuff. I'll just write the code, and I'll just tell you how to think, like whatever I am thinking while solving the problem. So permutations, basically what I can do is for any given n numbers, the permutation is npr, right? npr. So yeah, so basically if I tell you to write on a piece of paper all the permutation of, let's say, this example, which is 1 2 3, how are we going to do that? We'll first write all ones, right? 1 1. Okay, then we can write, so basically we'll write 1 2 3, and then after that all the permutation which was possible from 2 3, we can append it to 1. If we write 2, then all the permutation which was possible from 1 3, we can append it to 2. So basically this is exactly what even recursion should do. Like if we are able to write, if we are going to write a code, we should think it in that manner only, right? So yeah, so let's take nums.size. Okay, and then we can take a vector ntemp, which will kind of store every combination, like every permutation, right? So, and then we'll call, so we can start with 0, then n, then what else do we need? I think yes, then we can take temp and nums. think this one should be enough. Then we go here, basically int, this is the index that I'm standing on right now, and then I have vector int temp, and then I have vector int nums. Okay, cool. Now, so you can write base cases first, that is also fine, or you can directly write the transition, like how, you know, from this, how the child functions will look like. So as I told, basically I can take an index I, right, and I'll go to every index, right, and first I'll push this in my temp, because this is going to store my permutation. So I'll just push this. Remember that, as you know, this should be there for backtracking, right, and then I go I plus 1, right. I ask my recursion to give me other combinations, right, and we can pass everything, right. But the thing is, this nums array, right, so just imagine ki you are trying to print all the permutation and you gave the same nums array again, right. You for, let's say for I, right, if you are at 1, okay, it needed 2 3 when it goes to I plus 1, that is 2 3 array. For 2, right, for 2 it requires 1 and 3 as an array, so that it can do all the permutation of 1 3 and attach it to 2. How can we do that? So basically what you can write is a swap state. So basically whatever index that you pushed, we can swap that index with the index that we are currently at. So I think this step will do that thing that we require. Okay, again, while coming back, we'll need to reswap this thing. So I think if you write like this, or even if you write the same thing, it doesn't matter, right? So that is fine. Now the base case, right? So base case is basically, this is where you know, you should be a little careful. In fact, you should be careful at all the times while writing recursion cases, because it will be very difficult to debug after that if your program is, you know, going into some null pointer exception or something. So let's say when we reach to the end of it, let's say we don't have an, you know, any element in the array. So what do? We return, right? Is there anything else that required? I think not. Let's run this. Let's see what happens. Okay, cool. Oh, this should be index, right? And then I goes in, yeah, okay. This should be index, yeah. That, okay. What is this? Nums of I should be, yeah, swapped. This is I plus 1, right? Yeah, we go to I plus 1, and this index, oh man, what have I done? Come on. Okay, I'm getting wrong answer. Okay, this is not even print. What the heck? I should push all the way. So answer dot push back the temp that I have. Basically, I have found one 1, and that should do it actually. So you saw, like, I don't have to try for all the recursion tree, and I don't have to think. Basically the simple step for a recursion for a permutation is, let's just push everything at once, and then you just need to pass the remaining elements array, right? So you just swap that index, and then when you pass it, this will take care of you know attaching all the other permutation. What will be the time complexity of this? So for every recursion call, we are making another n recursion, or you can say n minus I. So that is like n into n minus 1 into n minus 2 until you reach the end, like when there is just 0 elements. So that is exactly like n factorial. So as we were writing on a piece of paper how to write all the permutation, is the same way. Okay, let's move on to the next problem. I think this should update. This is probably this should be an easy one. So given an array, we can use unlimited number of times, any number we can use unlimited number of times. Two combinations are unique if the frequency of the okay given an array of distinct integers and a target integer return a list of unique combinations. Okay, so basically this problem in DP would be like, how many times you can perform, you can make a sum like this. Okay, but here we need to actually print the combinations. Yeah, so here we need to print the combination. If you see, these are very small, so they want us to use the recursion. Okay, so here also we'll do something like f. So let's see how do we come up with an answer. We can have an f, we'll have an int, we'll have a n, which will be the end, just the size of the candidates, or whatever it is. And what else do we need? We need vector int temp, and then we need vector int the numbers that we want. I think, is that enough? Oh no, we need to have some value to store our current sum, right? So let's call it like current sum, and we also need a value to store our target, right? So that we can compare our current sum with the target. Okay, cool. Let's come here and let's write n is equal to num stuff size, right? So let's rename this as nums. Okay, what else do we want? We want a vector temp is the same way what that vector was doing, and I think that's it. So you pass 0 and current sum as 0, and then you pass target as target, nums as nums, and okay, we should change it actually now, and then we can return our answer. So okay, so now we need to think of a uh, the recursion transition, you can say. So okay, okay, here we can definitely do some you know, that idea of, you know, taking the element or not taking the element. So yes, so let's say uh, I take this element and I take this element nums of I. Okay, the thing is I can again take this element, right? Because we have unlimited supply. So I take this element and I stay here. I take n, I add this element in my current sum, target remains same, nums is also same, and temp is also same, right? And okay, we take this element in our and we stay at this point so that next time also we can use this element. Now let's say if I don't take this element, so I move ahead, so I do like temp dot pushback nums, sorry, what is this, sorry. So I could have just used the down arrow, but let's say if I don't take this element and I just move ahead, right? So I go like this, and before doing that I should pop back this, because my sum can start from any other index as well. So okay, so I think yeah, this should work. Basically I include this and call my recursion to find the remaining sum, right? And then if I don't take it, then the current sum remains same, and this should work. Now if the current sum is greater than target, or if we are able to reach I equals to n, right? So in both the case we return right, and we can write if current sum equals target, then also we return, and we push the current temporary vector in first. I think this should work, yes. Not sure though. Okay, this works. Okay, I'm not sure. Oh, okay, cool. So the idea here was very simple. You just take this element or you don't take this element, and I think this was pretty easy to even think upon. Think by yourself, right? But this permutation thing, definitely this is not a medium. If you come across this, this is just because this is a medium because it's a standard problem. Everybody talks about this, but I don't think it's pretty easy to come up at a first time. Okay, this is same thing. Okay, so here we could use unlimited number of times, and here we just need to use only once. Okay, and we could have used the similar code, right? We can use this. So we just, I think if I change one piece of line, one line, I think this should work. Let's see. Just bug me out. Okay, cool. We need to change this, right? We need to change this, and Yes, since we can only use one element once, we are going to move away from this element so that we pick up a new candidate, and if I don't take, then I just move ahead. So is that right to think? I think, is that it? Oh, okay. Yeah, this was, I think, expected. Once again, is find all unique combinations. Okay. So, okay. Okay, so we need to find unique combinations. So right now, if you see, I'm getting all the combinations. 1, 2, so 1, 2, 5, right? Even this, from this one, if another thing is possible, yeah, I'm getting 1, 7 as well. Then if you see 1, 6, 1 also I'm getting. So all the permutation which, all the combination which is possible from this one is picking up. Now how do we do the unique thing? So basically it just wants 1, 2, 5 and 1, 1, 6. So it wants in a order. So I think if I sort this, should it work? If I sort this, no, if I sort this also, if I sort this, then will it work or not? 1, 1, 6, 1 to 5. So let's say if I sort this, right, then I will always start from a smaller number. I think, okay. Yeah, that was my thing. Yeah, now we are getting 1, 2, 5, 1, 2, 5 two times, because if I print the sorted nums, so if I print the sorted nums, it will be, yes. So from this one there is 1 to 5. From this one also 1 to 5 is there. So that's what the extra thing is. So now I think there are two ways to get this sorted. So one thing I think we can take a set of vector and just store it in the, so basically we know that set will store all the unique vectors, and then 1 to 5 will not repeat twice. But I know that there will be a chances of TLE. I think there will sure be a TLE. So st.insert, sorry, not st.insert. This approach is not efficient anyways. So I do push answer, not push back this vector, right? So I think this should give me the right answer. So by sorting, we kind of, maintain the order, that from 1 to 5. Earlier, since everything was not sorted, I was getting even more combinations. So like 1 to 5, I was getting 2, 5, 1, 5 to 1. Everything, even those things were giving me. But let's submit. I think this will TLE because we are doing unnecessary recursion calls here. Exactly. I plus 1. Yeah. So this is TLE. So this I plus 1, right? we can optimize here. So what I'm saying, ki just go to the next index. I'm not saying go to the next different index. If I say that, that will work. So j less than n, j plus plus. If I find nums of I is not equal to nums of j, then I do this call and I break, because yeah. So the observation here is key. Here also I was going to a different number, but this time I'll go to a different number which is different. Basically I have sorted, so if 1111 is there, I'll just go to the next different number, which is 2. If after 2 there are more 2s, I'll not call again from that index where 2 was there and plus 1. I'll not call that. I'll call for a different index. And what happens, how do we maintain the count, because there are 1111, there are 51, so that will be taken care here only, because we are moving ahead from here as well, right? So let's say if there are 3 ones, or like here 2 ones, so this 2, so we are not missing this call, like we are not missing using this element, we are using that as well. Only thing is, before that we were making similar kind of recursion calls. Yes. So if you see, so I was going here and I was calling the same recursion call, and that's why this TLE, because this was 1. From this 1 still there was a recursion call with I plus 1, and then again there was a recursion call from I plus 1, which is the same call, right? Only current sum we are not updated. But if we do this will run. The thing is, we'll just call once this and we are done. Yep. So it's pretty hard to actually, first of all, this is recursion, and then if you think of an optimization, oh my god. Okay, this is like, should be the most advanced version of all these combination sum. Okay. Find all valid combination of k numbers that sum up to n. So the following condition. Okay, so basically here they have not given us a candidate array or something. Basically our candidate array is an array of digits, which I think we'll be using. Let's call it like digits, and we can just, so basically we are supposed to use only then what can we do? Also, I think we'll need just to store our answer, and in similar fashion I'll call. I have n. Now here there are actually more things to consider. So okay, basically n is our target, right? So we want to sum up to n. Yeah, so this call target is n, and we have a cap, we have a upper cap on selecting our elements as well. So I think this should not be very hard. So we can have things. So let's say have our counter. So this counter will be like how many number of elements that we have taken. We'll have our current sum same to maintain our current sum. Let's have it like here. Okay. And okay. Do we need digits? No digits, we can take it from up only. I, N, and what? Counter, and yeah, of course, temporary vector to store our current combination. And then I call n. So I start from 0, I go to n. Okay, so n here will be 9, right? Because we are our array, the candidate array is kind of digits. Okay, cool. Current sum is 0, and then we have a counter which is starting from 0. So everything is kind of hard coded here. Okay. Now I think this is now pretty similar to what we just did before. So it's again with the same idea of including or not including a digit, right? So if I start from, let's say, okay, sorry, let's say I used a digit, right? So I use this digit for digit. So I use an ith digit, and then since I can only use it once, I move ahead, and my current sum goes to digits I, and then my counter increase as well because I have chosen an element. My temp is as, if I don't take this digit, then what happens? I think it's simple. No, I move ahead because I'm not allowed to, so I take it, I move ahead. If I don't take it, I just move ahead, and then plus, no plus, then counter also remains same, and temp also remains same. Yeah, I think this should be a proper recursion transitions. What is the base case, right? So let's have a base case, and the base case will be, I think, I same. If I reaches n, before that let's write this base case. So if our current sum equals target, right, then we return, and then we do answer dot push back this temp as well, right? Or what do we do here? We do if our current sum is greater than target, or our counter goes greater than k. Oh, so we didn't take k here. We forgot to take k. Now here also counter k. Okay, cool. And this is our k. I think this should work now. And here, if that happens, then we return. Is that right? We didn't take target. Oh, we didn't take target as well. Oh man, what are you doing? Okay, let's just take target. I think these are the things that we... target neighbor chains. Let's see if that works. Okay, this is our counter. I hope there is no more typos. Oh man, come on, what is this? If declared here, too few arguments to call. Why did it use 1 again? 2 5 and oh, okay. Shit. But it was using 1 again, right? No, now it's fine. Why was it using 1 again? Anyways, let's try submitting this. I got confused with the wrong answer. Yeah, this is right. Okay, cool. I think this is pretty cool. We covered up in like really good amount of time. Okay, thank you.